All right, now to talk about the chain rule. So picking up where we left off, let's start off kind of just, yeah, let's start off by looking at a function that's outlined in the notes. We have w equals x squared y minus y squared, right? But this time we're actually told that x and y are functions of another variable t. So in the example, we have x is equal to sine of t and y is equal to e to the t, right? And we want to figure out what dw dt is. Notice I'm using a regular d and not the partial d when t is equal to 0. Okay, so first off, remember this notation implies that w is a function of just one variable, t. But we can see here that w clearly is a function of two variables, x and y. Both of those happen to be functions of t. Um, Before I talk about chain rule stuff, one thing that we can do is we can actually find or rewrite w so that it's only in terms of t. Anywhere that I see x, I could replace that x with sine of t. So we get sine squared t. And then anywhere that I see a y, I can replace with e to the t. So e to the t minus e to the 2t, right? Because remember, this will be e to the t and then squared, power to a power you multiply, which is why I got 2t. So if I were to take the derivative of this with respect to t, that would give me dw dt. And I would be taking a regular derivative, what we would call an ordinary derivative, as opposed to a partial one, because now w is written as a function of only one variable, t. So if I were to do it this way, right, it would involve a couple of things. First off, product rule for that first term. Then when I go to take derivative of the first factor, I have to use chain rule. Should give me 2 times sine of t times the derivative of sine of t multiplied by e to the t plus sine squared of t multiplied by the derivative of e to the t, which is itself, minus the derivative of this exponential. Note the derivative of 2t, we get 2. So 2e to the 2t. And this would be our dw dt. However, we can also use partial derivatives. And actually, let's finish the question before I talk about that. All right, so then I could plug 0 in for t. Lucky for me, this is going to end up, a lot of terms are going to end up zeroing out, right? Because remember, sine of 0 is 0. So this term, this entire term is 0. This entire term is 0. This is -2 times 1. So we end up getting -2 for dw dt when t is equal to 0, which you've also learned you can write as w prime of 0. So if I were to take this same function, I could actually use partial derivatives in what we refer to as the chain rule. Yeah, and what we refer to as the chain rule for partial derivatives. The actual rule itself, we have dw dt is equal to the partial of w with respect to x times dx dt plus the partial derivative of w with respect to y times dy dt. So when looking at this rule, the first thing I want you to kind of notice here is when I'm using the partial derivative versus the ordinary, right? So for dx dt, dy dt, we're using an ordinary derivative because both of those are functions of just one variable, just t. That's the only independent variable there. With w though, we're using partial derivatives because w is a function of both x and y, right? And the overall thing is an ordinary derivative because as you saw here, we can actually rewrite w in terms of only one variable if we choose to, namely the variable t, which is what we used in the ordinary derivative. Okay, so I don't really like you to think that you're canceling anything out here because that's technically not what you're doing. Right, you're just multiplying two rates by each other. And the product of those two rates just happens to give you what you're looking for. Really notice here though that you would end up with a partial derivative that comes from the x side plus a partial derivative that comes from the y side. And that's actually how this formula is kind of derived, right? From the assumption starting off that w is equal to some function of x times x plus some function of y times y, right? And then when you take the derivative of that, you end up with something like this. Um, but yeah, we could actually use this to do what we did up here without all the complicated, remember your Cal 1, this, that, all blah stuff, right? And I mean, sometimes it's easier, sometimes it's not. This is really just a stepping stone for the part that's going to be more interesting, right? But let me show you how this would work. So to figure out dw dt, I need to know four things. Okay, I need to know the partial of w with respect to x. We can find that. Right, so that's going to be 2xy, and the derivative of that term will be 0. We need to know the partial derivative of w with respect to y. Okay, and again, derivative of that first term will just be the number x squared. And derivative of the second term will be 2y. So that's what we get for our partial derivative of w with respect to y. We also need to know the ordinary derivatives, dx dt and dy dt. So dx dt, if I look back at what x is sine of t. Derivative of sine of t is cosine of t. And then if I look at what y is e to the t. Derivative of e to the t is e to the t. So dw dt would be equal to partial with respect to x, 2xy, multiplied by dx dt cosine of t, plus partial with respect to y, which I'm going to put in parentheses because it has two terms, times dy dt, which is e to the t. And you might be thinking, well, this is weird. There's x's and y's and t's, oh my. And yeah, I mean, if you really want to, you can replace the x's with sine of t's and the y's with e to the t's, and you'd end up getting, yeah, and you'd end up getting the exact same thing we got here. Right? But if I know that my end game is just to figure out what dw dt at a certain value is, then I don't really need to go through that intermediate step. Instead, I could figure out what x and y are when t is 0, which would be fairly easy, right? Because if t is 0, then x is sine of 0, and that would just be 0. So x would be 0, and then y is e to the t. E to the 0 would be equal to 1. So if I plug all of those values in, I get 2 times 0 times 1 times cosine of 0 plus 0 squared minus 2 times 1 times e to the 0, right? Which is going to end up giving us the same thing, -2. So you see, we could use partial derivatives to essentially carry out the chain rule, which this derivative involved heavily. Now, it gets more interesting when we talk about functions that have more variables. So the next part of the notes, we kind of talk about what it would look like if x and y were actually functions of two variables themselves. So actually, before we do that, there was another example that I completely skipped over. Yep. All right. So before I start talking about x and y having more than one variable, let's look at an application. So let's say that we have two objects that are traveling in elliptical paths, like maybe perhaps a planet. And the paths for the objects are given by sets of parametric equations, which basically give you the x and the y coordinate as a function of t. All right, so we have a set of x's and y's for each of the two objects. Based on this, it says at what rate is the distance between the two objects changing when t is equal to pi? So looking at what I'm being asked for, I want to know the derivative of the distance between the two objects with respect to time. So this is going to require our distance formula. So if you remember, distance formula is essentially just Pythagorean theorem with changes in x and changes in y. And we can write it as the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. So looking at this, I really don't want to do regular chain rule with that because we'd have a chain rule, and inside that we would have two more chain rules. So instead, what we can do is we can use our partial derivatives to make this a little easier for us. All right, so using our chain rule, we know that this can be written as the partial derivative of the distance with respect to with respect to x one times dx1 dt, all right, plus the partial derivative of the distance with respect to, and then we can do that for x2 as well, times dx2 dt. And we need to take care of the y's as well. So basically we have one term for each of the different variables that we have in that equation. If you notice, this is a function that has four variables. So we're going to have four terms in our chain rule. So partial of the distance with respect to y1 times dy1 dt plus the partial of the distance with respect to y2 times dy2 dt. Okay, so now that we've written all that out, let's take a look at these different derivatives. Yeah. Okay, so first one, this partial derivative with respect to x1. Remember, that just means that x1 is the only thing that is actually a variable here. So this is kind of like if we took the square root of number minus x squared plus a number, right? So we would start off with our regular chain rule, 1/2, take the inside of your square root, does not change. Take one away from the power, and then multiply by the derivative of the inside. Luckily for us, x1 is the only variable on the inside. So the derivative of this term is all that really matters. So that derivative would be 2x2 minus x1. Times -1, because the x1 has a minus in front of it. All right. So when I simplify that, the 1/2 times the 2 will give us 1. And basically we end up with negative, or with, we could write a negative where we could just swap these either way. x1 minus x2 over the square root of all that. Now, other thing I want to note here is that okay, we know that in this case, t is equal to pi. So if I can figure out what all of those x and y values are at those points, then that could actually help me figure out what this derivative is at that point, because that's what matters. So we know that when t is 0, x1 is going to be, right, 4 cosine of 0. Cosine of 0 is 1, which means x1 is going to be 4. x2 is going to be 2 times sine of 2 times 0, which is going to be 0. For y1, that's going to be 2 sine of 0, which is 0. And for y2, that's 3 times cosine of 2 times 0. Cosine of 0 is 1. Multiply by 3, we get 3. So the only variables, well, the only coordinates in this scenario that are non-zero are just x1 and y2. So with that, it makes it a little easier for us. We know the numerator is going to be 4 minus 0, which is 4. And in the denominator, we have the square root of 0 minus 4 squared, 16. And 3 minus 0 squared, so plus 9. And 16 plus 9 is 25, which means that this is square root of 25, 4 over 5. So that partial derivative has a value of 4/5. Now to get dx1 dt, we know that x is 4 cosine of t, so its derivative will be -4 sine of t. And again, if we consider this only at the value when t is equal to pi, wait, this was pi, not 0. That doesn't actually change much, it just means This will be a -4 now. There we go. So that's a pi, that's a pi. Since that's doubled, that stays positive. Yep. Okay. So anyway, when t is equal to pi, this ends up having a value of -4 sine pi, which is 0. So that whole first term will literally be 0, which is actually a trick that you should take advantage of in a question like this, because notice all of your x's and y's were trig functions that are evaluated at pi, which means some of them are going to be 0. So with that in mind, let's actually take a look at all of the other coordinates and their derivative with respect to t. So x2, we would end up getting 4 cosine of 2t. If I evaluate that when t is pi, cosine of 2 pi is 1. So we get 4. I should not box that. I'll underline it. Now, if I go through with y1, right, we know that y1 is 2 sine t, so its derivative will be 2 cosine t. If I evaluate that when t is equal to pi, we know cosine of pi is -1. Multiplied by 2, we get -2. And then for the last one, we know that y2 is 3 cosine 2t, so its derivative will be -6 sine of 2t. If I plug in pi for t, right, then I know sine of 2 pi is 0. Times -6, we get 0. So the point of going through and doing all of these first is if we look back at our chain rule here, we know that this term is going to 0 out because we're multiplying by 0. We also figured out that this term is going to 0 out because we're multiplying by 0. So really the only partial derivatives I need are partial of distance with respect to x2 and partial of distance with respect to y1. So because we went through and kind of did that already for x1, they're actually going to take fairly similar forms. So again, we would have to bring the 1/2 down. We would keep the inside the same. We would take 1 away from the power. And then we would multiply by the derivative of the inside, keeping in mind that x2 is the only one that matters. So with that said, I don't care about that. I just care about this part. So bring the 2 down, I get 2 times x2 minus x1. Since the coefficient of x2 is 1, I don't have to multiply by anything else. And just like before, the 1/2 and the 2 multiply to make 1. So this partial derivative is essentially just x2 minus x1 over the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. Now, if I plug in the values for each of the coordinates like I did back at this partial derivative, we know that x2 has a value of 0, x1 has a value of -4. So the numerator will be 0 minus -4, also known as +4. And because there's literally nothing different about this, we know that this is also going to work out to 5. So 4/5. Now moving on to the other partial derivative we need. All right, we've got partial of our distance with respect to y1. So for this one, again, it's going to kind of take a similar form. 1/2, keep the inside the same. Take one away from the power and multiply by the derivative of the inside. But this time, y1 is the only variable that matters. So we're going to multiply by 2 times y2 minus y1. Since y1 has a minus in front, we have to multiply by -1. And just like before, 1/2 times 2 will give me 1. So this will work out to, we could either write the negative sign or we could switch the order. y1 minus y2 divided by the square root of all that same stuff. Okay, we already know the denominator is going to work out to 5. I'm not even going to care about that. All right, but with y1 and y2, we do need to figure out what the coordinates are when t is equal to pi. So if I go back and look, right, y1 is 2 sine of t. So 2 sine of pi gives me 0. For y2, we have 3 cosine of 2t. So if t is equal to pi, this would end up just giving me 3 times cosine of 2 pi, which is 1. So altogether, that ends up being -3/5. And again, because dy2 dt ended up being 0, we aren't going to need to figure out that partial because that term will end up being 0. So using the parts that are remaining, we know that the rate of change of the distance with respect to t is going to be equal to the partial of the distance with respect to x2 times dx2 dt plus the partial of the distance with respect to y1 times dy1 dt. If I plug in the numerical values that I found for each of these, we know that that partial for this one worked out to 4/5. We know that dx2 dt worked out to 4. Partial with respect to y1 worked out to -2. And dy1 dt worked out to, wait, no, well, that was actually this one. Right, so that's -2. This one is -3/5. Okay. So if I multiply all of these together, I get 16/5 plus 6/5, which gives me 22/5. And that's the answer. And that was humdinger. Okay, so now getting back to what I was talking about earlier about when x and y are in terms of more than one variable. So it's like a parametric equation of two variables. Yeah. Right? Straight away, you can figure out the partial derivatives with respect to each of those other variables, parameters, kind of in a similar way, except now we don't actually have any ordinary derivatives because nothing is a function of just one variable. So if I wanted to, so let's say that we know x and y are both functions of s and t. Right, so s and t are parameters. If I wanted to find the partial of w with respect to the parameter s, then I would just need to take the derivative partial of w with respect to x times partial of x with respect to s. That gives me the x part of the derivative. And to that, we would add partial of w with respect to y times partial of y with respect to s. And that gives me the y part of the derivative with respect to s. And if I wanted to do this for the parameter t, I would follow a similar formula, right? I would start with partial of w with respect to x times partial of x with respect to t. That gives me the x part. To that, I would add partial of w with respect to y times partial of y with respect to t. That gives me the, whoops, that should be curly d. There we go. All right, and that gives me the y part of this derivative. So you can think of it as you get a contribution to the derivative of w from x and from y, and you're adding the contributions together. Really, that's all the chain rule boils down to. It's just knowing it's just knowing what is defined as the parameter versus what's defined as the variable that's in the original function, right? Once you've kind of squared that out, it's just remembering to multiply these together, and it forms kind of this chain reaction. I get the x part, I get the y part. So, with that said, let's say that we want to use the chain rule to find the partial with respect to s and with respect to t for this function. W is equal to 2xy. We are told that x is defined as s squared plus t squared, and that y is defined as s divided by t. So if I wanted to find the partial of w with respect to the parameter s, I can write my chain rule out. I got to get the x part with respect to s, and then I got to get the y part with respect to s. Oops. Okay. So with that said, the partial with respect to x would just be 2y. Partial of x with respect to s would just be 2s. Partial of w with respect to y, we would get 2x. Partial of y with respect to s, right, we would get 1 over t. So cleaning that up a little bit, we get 4ys plus 2x over t. Okay, now the question itself asked us to find, the question itself just asked us to figure out the partial derivatives. It didn't give us a value to plug in for s or for t, which means that we won't be doing the find out the x and the y and plug all the numbers in. We just want to get everything in terms of s and t only. So if I see my original variables hanging around, I can replace them using these definitions. So anywhere I see y, I can replace it with s over t. Anywhere that I see x, I can replace with this guy. Right? And if I wanted to clean that up a bit, this would be 4s squared over t. That's also over t, so I can add my fractions already. If I distribute that 2, I would end up getting 4s squared plus 2s squared, so 6s squared, and only 1t or 2t squareds in the numerator, right? Because we distribute the 2. And this is all over t. And that's the partial with respect to s. Easy peasy. Now, if I want to find the partial of w with respect to t, I would do a similar thing. Right, I would go through and write out my chain rule. So again, I need the part that comes from x plus the part that comes from, oops, the part that comes from y. And I could just grab the partial derivatives from various parts that I've already done, right? So for example, this one I know is going to end up being 2y. dx dt is going to end up being 2t. I already know that's 2x, and dy dt is going to be the, yeah, negative s over t squared, right? Using our power rule. Remember, that's s times t to the minus 1. All right. So if I were to clean this up a bit, I would end up getting 4yt minus 2xs over t squared. And again, we don't have numbers to plug in for s and t, which means we're not looking for a numerical answer, but I am looking for an answer that only involves s and t. So anywhere that I see y, again, I'm going to replace with s over t. And anywhere that I see x, I'm going to replace with this guy. All right. And doing a little bit of algebra. Remember, I need to have a common denominator to add these fractions. So I have to multiply top and bottom by another t so that this will have a denominator of t squared, right? Since that t was already there, multiply by another t, that is squared. Yeah. And then if I distribute the 2s, I end up with 2s cubed plus 2st squared over t squared. And this minus technically means that I could write that as plus and then change the sign on these terms, which would be helpful. And then I see I have two like terms I could combine. So that's going to leave me with 2st squared minus 2s cubed over t squared. And that would be the partial with respect to t. Okay, one last little topic here, right? So we can actually use partial derivatives also to do implicit differentiation. So to start off with, let's say that I have this equation. And this one is also in the notes, right? And let's say that I want to solve for dy dx by using implicit differentiation. Remember what that actually means. So if I want to find dy dx, I'm going to take the derivative of every term, but everywhere that I see y, I know I'm going to have to technically use chain rule and multiply the derivative by dy dx. So y cubed would be 3y squared dy dx. And if you think about it, it's because y is something that involves x. So that could be like 1 plus x minus x to the fifth, all squared, right? It's just we don't know exactly what it is, which is why we do that. Okay, and then here, derivative of y squared, we get 2y dy dx. Derivative of minus 5y would be minus 5 dy dx. Derivative of minus x squared is negative 2x, and derivative of 4 is 0. And of course, the derivative of 0 is also 0. So remember when you did this in Cal 1, the approach was to take anything that didn't have a dy dx in it and move it to the other side. That way, everything that's left over, right, has a dy dx as a factor. So you could factor out dy dx. And with that done, all you have to do now is just divide by the other thing. So we would get that dy dx is equal to 2x divided by 3y squared plus 2y minus 5. And that's dy dx. So that's what implicit differentiation looked like as a Cal 1 problem. We actually have a definition. Well, it's a formula that can also be derived that involves partial derivatives to make implicit differentiation, in many cases, easier. So the formula is dy dx equals negative fx of xy. Remember, that's partial with respect to x, divided by fy xy. That's partial with respect to y. So what are we taking the partial derivative of? Basically just the left side of that equation. The rule, though, is that you have to have one side equal to 0 for this to work. So if I let capital F, just the original, no derivatives taken yet, be equal to that left side. Okay, I can find fx and fy pretty easily. Ah, silly, silly. All right, so I know that fx will be my derivative with respect to x. 0, 0, 0, negative 2x, 0. Fy, it's my derivative with respect to y. So 3y squared, don't need the dy dx anymore. 2y minus 5, 0, 0. So now that we have both of these first partial derivatives, I can get dy dx by doing negative derivative with respect to x, so minus 2x, divided by derivative with respect to y. And if we multiply those negatives, you know what we get? We get the exact same thing that we got up here. So we can actually use partial derivatives to do implicit differentiation. And that also works when we have functions of more than one variable, right? Or more than two variables, right? So you can actually have similar formulas for functions of three variables. If, for example, I wanted to figure out, yeah. So if, for example, I started off with this equation, Okay. I could actually use implicit differentiation to figure out d or partial z with respect to x. Right. And I could do that pretty much in the same way that we've done implicit differentiation, right? So I would take the derivative of every term, right? If I see an x, I take its derivative like normal. If I see a z, I remember that that is a function of x. In this case, if I see y, the one that's left out, I treat it like a constant. So with that said, if I take the derivative of that first term, I have 3x squared times something that is a function of x, which means I have to use product rule to take the derivative of the first term. So I would get 6x times z plus 3x squared times the derivative of z, which would be partial z with respect to x. For this one, since y is a constant, this is just a number times x squared. So I bring the number down, or I bring the power down, and we get 2y squared x, or 2xy squared. I can write it either way. When I see this one that has a z, remember z is something that involves x, so I have to use the chain rule on that term. So that would be 6z squared times the derivative of z, which will be partial z with respect to x. And here I have a number times z. Derivative of number times z would be the number. But again, since that's z and not x, we have to multiply by partial z with respect to x. Derivative of 5 is 0. Derivative of 0 is also 0. And then we can do basically the exact same thing that we did with implicit differentiation, where we move over anything that does not have the derivative so that we can factor it out. So I see that I'll need to move, or I'll need to add 2xy squared to both sides. And I will need to subtract 6xz from both sides. And then when I take those out, notice all the things I have left have partial z with respect to x. So just like before, I could factor that out. And I would leave behind 3x squared from that term, 6z squared from this term, and 3y from this term. And then if I divide both sides by this factor, I end up getting my partial derivative. Now, there actually are similar rules that we could use with partial derivatives to simplify that process. And here are the rules. If I want to know the partial of z with respect to x, I would get negative partial with respect to x over partial with respect to z. Similarly, if I want to find the partial of z with respect to y, I would have negative partial with respect to y over partial with respect to z. Okay. So if I wanted to look at that exact same equation, right? Remember, if one side's equal to 0, then the other side of the equation is just regular f. So f of x, y, and z, we can write that down. Okay, we can write that down, and now I can look at these partial derivatives. So Let's say I want to find partial z with respect to x, which is what we did back here the old-fashioned way. I would need to find the partial derivative with respect to x of this. So that would be 6xz. Notice I don't need to multiply by dz dx minus, I'm going to put this in parentheses, minus 2xy squared. This will be 0 because there's no x. This will be 0 because there's no x. This will be 0 because there's no x. Then in the denominator, we take the derivative with respect to z. So 3x squared, right? Because that's a number times z. This doesn't involve z, so derivative is 0. This will be 6z squared. This will be 3y. And that's 0. Okay, now if I distribute this negative to both terms, guess what we get? The exact same thing that we got up here. But it moved a lot faster, and we didn't have to worry about those pesky dz dx's to be able to get our derivative implicitly. Now, for fun, and because the problem asked for it, let's figure out dz dy, partial z with respect to y. Why not? So we would have derivative with respect to y in the numerator. First term would be 0. There's no y in that one. Second term, we'd bring the 2 down. We would have negative 2x squared y. 0, 3z, 0. And partial with respect to z is going to be the same as it was before. That didn't change. Right, and if I distribute that negative, I end up with 2x squared y minus 3z over this denominator. And that's our answer. And now we have both partial derivatives in a fraction of the time. So basically, remember when you get partial derivatives that involve the chain rule, you're typically given some kind of parametric equations for your independent variables in the original function. So in the examples we did, x and y were defined in terms of parameters t and or s. So if I want to find the derivative with respect to one of those parameters, which oftentimes is something I want, right? Like in physics, economic, like anything that uses functions of more than one variable, this is applicable. Basically, I have to remember that for every independent variable in the original function, I'm going to have a term in my chain rule, right? So if x and y are my only variables in the original function, then that means, yeah, then that means that I'll have a term that gives me the x part and a term that gives me the y part. And then I add them. And then you can do that for as many variables as you need to. And we also learned that we can use partial derivatives to do implicit differentiation, which actually is pretty cool and honestly a lot less of a headache than doing implicit differentiation. So take that knowledge and go do your homework. Happy mathing.